This week we will learn about properties of light and instruments that use light. But this time around we're going to get a little deeper into what light is. Not only are we talking about the part of the electromagnetic spectrum that's visible to our human eye, but also we will go all the way from radio waves, yep, that's light, through infrared, visible light, ultraviolet, X-rays, and all the way to gamma rays, and how we are actually able to collect that information. So in the last lecture we learned about the history of our understanding of light from antiquity through the Arab Revolution and Newton ray optics. We also included Romer's measurement of the speed of light, Bradley's stellar aberration, and Fizeau measurement of the speed of light. But beyond just measuring that speed, there's plenty more that we can learn about light. We're starting today. But you may say, why are we talking about light at all? After all, we advanced all the way from the understanding of antiquity about the stars through Newton's understanding of physics and how he tied it together. Well, two things happen in parallel: our understanding of light and our understanding of astronomy. But really these are the same exact things. Because the big question is, what is science? What is a scientific theory, so to speak? And in both cases, as you've seen, as you will see, very careful observations fit something that has some connection with mathematics. Why it is that way, we do not know. Nature speaks in the language of mathematics, so it seems. For the time being, that is our understanding of the universe. Tomorrow morning, that may change. But this is what science is, that big and very extensive body of knowledge that we as humans collected for a few thousand years shows us this amazing connection that we never expected. It was at the time of Fermat, just before Newton, and then at about the same exact time as Newton, with a fellow by the name of Huygens, Fermat was French, that those two people assumed that light has a new type of property. Fermat said that light takes the shortest time to arrive from one point to the other, and Huygens has shown that light could act as if it was a wave. But neither had a very conclusive evidence. It was left to Young in the year 1801 and 1802 to conduct an experiment that proved that light behaves sometimes as if it was a wave. The picture shows how a wave coming as if from a pebble that was thrown at point A hits two openings. From each of the openings another wave comes out as if a pebble hit B and C, and when those waves come together, when crest meets crest, you'll see a bright spot, and where crest meets a trough you will see a dark spot. This interference pattern was the first support for the idea that light sometimes behaves as if it was a wave. Another property of light that works beautifully with the light being a wave is the change in direction when light moves from one medium to the other. This is apparent when you look, for example, at a spoon in a glass of water. The spoon, tilted on its side, looks as if it's kind of bent. That comes about because as light goes from one medium for example water, into another medium, air, the speed changes. In the picture below, this is the opposite. The light moves from air into water. As a result, in water it moves slower. The crests are lumped closer together, and in order for that to work, the light has to change direction. Now here is an example where light does change direction when it hits a flat glass, but then emerges as if it was going in the same direction, albeit with a little bend. That's a simple change of direction, but what if the glass was not flat, but rather in the shape of a lentil? Hence the word lens. As you can see, the ray on the right bends towards the left, the ray on the left bends towards the right, and light can focus onto a point. You can carve your name with a lens on a piece of wood by using sunlight and concentrating it this way, or you can use the same exact effect in order to magnify an image that is very far away. This picture is of the oldest known way of magnifying those faraway images. For example, images of sunspots or mountains on the moon, or the shape of Venus being crescent or phases, or the Jupiter satellites. All of these were observed by a fellow by the name of Galileo Galilei. Let us see a little bit closer at how magnification happens. Remember, we started with the properties of light that behaves as a wave. Therefore, the light going into the lens on the very left, into the objective lens, that light comes at an angle theta, a very small angle. As it leaves the lens, it's being focused onto a point after the big F on the focal plane, but it continues. The light that came from above goes to the bottom of the eyepiece. The light that came from the bottom goes through the middle of the eyepiece. These two rays go to the very sides of the eye, and then they arrive at our retina. You may notice that the light entering our eye lens and hitting the retina comes at an angle theta 2 that's much larger. Since it is much larger, the image is much larger indeed. But since it comes from the bottom, it also appears upside down and actually switched right and left.
Galileo Galilei, the first person to actually check on the so-called Newton first and second law, was also a developer of the early telescope. The actual telescope was invented as somewhat of a toy in the Netherlands at about the same time that Galileo lived. He heard about it, developed it, and used it for both commercial purposes and for his astronomy. The following is a telescope that I have used about 12 years ago in a university called Bucknell University. This is made by one of the most famous telescope maker family in the United States, the Clark family. Therefore, this is a Clark refracting telescope that's still actually working and is used by hundreds of people every month in observing planets. It's one of the best ways of observing planets. Interestingly, not as good at observing things like galaxies. Now look at this refracting telescope. On the left you have a picture of it with one big lens on the left and small lens on the bottom right. The weight on the other side just makes sure that there is no torque on the telescope and it doesn't fall. On the right hand side, the lady is actually observing with the telescope, but at the very back there is a plate. This is called a photographic plate. In the mid-19th century, people started using photography, and right away some of them put a film at the back of the telescope, as you can see here. Of course, this picture is not from the 19th century, but the method is the same.
Here is a fairly complicated one. Please think about that one for at least 15 seconds. Try and answer the following question. Because the bottom of the lens and the top of the lens, if you just look at them from the side, look like prisms, and because prisms create rainbows, problems with lenses may include okay, I'll whistle as usual. This example of a problem with lenses and telescopes, which is called chromatic aberration, is one of many problems that we will discuss in the next couple lectures.